In this module, we're going to learn about how to make ROC curves in STATA, while at the same time looking at a relatively hot topic in statistics and epidemiology right now, risk prediction. Alright, so consider the following hypothetical example. You are a doctor/statistician and you have the responsibility of telling a patient how likely he is to get coronary heart disease. So you're going to collect some prognostic factors, and based on that information, you're going to tell the patient he's either high or low risk. So how do you determine what prognostic factors to use and how to make this high or low risk decision? Well, using the Framingham data, you can predict the probability that an individual gets CHD given these prognostic factors, but you need some measure to quantify how good these predictions are. And so we can use an ROC curve to evaluate how good these predictions are. So how do we construct this ROC curve and how does it help us evaluate our predictions? Well, I did these steps for you because coming up with the prognostic score is going to be something we learn way later in this class in the final weeks. But essentially what I did is I used systolic blood pressure, number of cigarettes smoked per day, total cholesterol, sex, BMI at baseline, and then I predicted P, the probability of getting CHD for someone in the Framingham cohort. And then I selected a cutoff probability C to distinguish high-risk, low-risk patients. If P is less than the cutoff, the patient is low risk. Greater than the cutoff, the patient is high risk. And then I'm going to classify all patients in the data set as high or low risk. So now we can bring in the idea of sensitivity and specificity. For a given cutoff, I can take the probability that someone is high risk, given that they have CHD, and define this as sensitivity. And then for specificity, I can say the probability that someone is high risk, given that they don't have CHD, is going to essentially be 1 minus specificity. So as I said before, I've already constructed a data set for you that contains the sensitivity and specificity for a variety of different cutoffs. So now go into STATA and open the dataset roc.dta, the link is below this video, within STATA. Once you have the dataset open within STATA, click on the data browser. You can see that this dataset contains 7 different variables. For this module, let's only look at C, the cutoff, sensitivity 1, specificity 1, and the false positive rate, the first one. So we've got 17 observations, meaning that we've looked at 17 different cutoffs. For each one, we know the sensitivity, we know the specificity, and we know the false positive rate. So think back to class. What is an ROC curve? The ROC curve is a graph of the false positive rate versus the sensitivity, and really implicitly, it's for a given cutoff C. So we just take a bunch of different values of the sensitivity and the false positive rate, plot those against each other, and then we get an ROC curve. So let's do that now. To make a plot, we're going to go Graphics, Two-Way Graph, Create. We're going to make a line graph here. The Y variable, recall, is sensitivity. The X variable is the false positive rate. Now hit Submit. So you can see that on the X-axis we have the false positive rate. On the Y-axis we have the sensitivity. Now the first question asks us, how do the sensitivity and specificity change as the cutoff increases from 0 to 1? Looking at this graph, we can sort of think of this and we can see the trade-off pretty clearly. Increasing sensitivity is going to decrease specificity. To increase specificity, we're going to have to increase the cutoff. But by increasing that cutoff, fewer patients are going to be classified as high risk. But among those who are classified as high risk, we're pretty sure that those people are going to have a CHD event, unless they modify their behaviors. However, by increasing that cutoff, we now have more patients classified as low risk. Our ability to predict that a patient will not get CHD is now decreased because we have included higher risk patients in the low risk group by increasing that cutoff. All right, so that answers the question about the trade-off between sensitivity and specificity, but in practice, you're the doctor statistician, you have to make the high versus low risk decision. What value of C would you choose in distinguishing high risk versus low risk patients, and why? So looking at this graph, we want to balance sensitivity and specificity. So I want to make sure that my false positive rate is relatively low. Maybe we'll say we want to keep it below 0.5. Sensitivity, we want to make sure that's relatively high. Essentially what I have to do is I have to pick a point on this curve that as the doctor statistician I think is reasonable. Now in the context of this problem, We know that a patient could modify lifestyle risk factors, and therefore it might be more practical to select a higher specificity than sensitivity, because telling a patient that he is high risk and being wrong is less severe of a mistake than telling a patient that he is low risk and being wrong. So that's a brief introduction to how to make an ROC curve in STATA and how to interpret those ROC curves in a real-life application of risk prediction. To learn more about this risk prediction setting, see the next module.